Okay, well, welcome to our second session of the symposium today. You'll hear 4 different talks in this session that is focused on broad patterns of habitat restoration and how we can monitor them. You'll be introduced to some useful tools of the trade that apply to any coastal restoration project, including remote sensing and surface elevation tables. We'll then hear about how groundwater influences marsh restoration success. And finally, we'll end the session with a talk about seagrass habitat restoration at Hester, again with techniques applicable to any West Coast marsh. So our first speaker in this session is Charlie Endris. He is ESNR's geospatial specialist, a contractor through Moss Landing Marine Labs, who's been working at Elkhorn Slough and Moss Landing Marine Labs since his master's thesis on bank erosion in 2009, where he did terrestrial laser scanning. And he's really an asset to our team, bringing skills in the field and with GIS. So, Charlie.
Thanks so much, Kirstine. It was a great overview of the project going on. Let's see, make sure I can get it. There we go. All right, so I'm going to be starting with showing you some surveying tools, some examples of survey tools that we use for monitoring the marsh restoration at Hester Marsh. You've seen this image before. This is Hester Marsh here in the foreground. Just a brief note, I'm going to be talking mostly about the topographic products that we're getting through these survey tools, and then my colleague Sean Mccollum will be talking about some of the imagery that we're developing from the drones that we're flying, and then the classifications that we're doing. So I'll go over some of the tools of the trade we're using for the survey gear, and then why our digital elevation model is important. And then I'll talk about how these DEMs are being created and how accurate they are. And then some uses for DEMs at Hester that we've had. And then I'll go over a brief case study of the surface elevation tables, the sets, and how they compare with the drone DEMs that we've got. So first off, we've got several different types of techniques we're using out at Hester Marsh, including some of the older survey gear, including transects and quadrats, some differential leveling, and some surface elevation tables, which I'll refer to as sets. And then we've also got some newer, more technologically advanced gear, such as the RTK GPS, the terrestrial LiDAR, and the drones. Drones increasingly have been part of our toolbox for the last 7 or 8 years, so I'll be primarily talking about the products coming from those. But moreover, all of these are really designed to measure elevation, which is really a crucial tool in understanding marsh health out there. So as you've seen this slide before that Monique showed, the DEMs are really pivotal for our understanding of how the marsh evolves over time. LiDAR is very useful in this scenario where you have broad spatial scales, a bit lower resolution, a bit lower accuracy, but it's really good for seeing these kind of high level or broad range tidal regimes. But what we really are after are these kind of finer scale, tighter elevation ranges, particularly after the marsh restoration was completed. So that's what we're seeing here in this imagery, where we're seeing elevation ranges in the 4 centimeter range. Our spatial resolution is about 1 to 2 centimeters. And what you can see in these cooler colors is about a 20 centimeter drop in the elevation of the phase 1 shortly after the tides were let in. And so without this sort of level of detail, we wouldn't be able to see that kind of these sort of events occurring. So for those of you that aren't familiar with drones and digital elevation models, this will give you a quick primer. Unlike aerial LiDAR or terrestrial LiDAR, which really uses that laser pulse, the time of flight of a laser pulse to determine positions on the ground, the XYZ positions on the ground. Structure from motion comes from these drone imagery. So as your drone is flying across a landscape, it's taking a series of images of the same thing on the ground, and it's using those to create this kind of three-dimensional scene. In the same way that your eyes are separated slightly apart on your head to give you depth and perspective, it's similar with these images. And so we'll capture about 1,000 images, maybe more, and that will be run through a processing software, and they'll create this really rich data set of XYZ values that will turn into a DEM model. In order to calibrate those models, we need what we call ground control points, or these GCPs, which are these bucket lids on the ground that can be surveyed and be visible from the imagery itself. And so we would lay these ground control points out in a grid. We would survey them before every flight. And we came up with this design based on an experiment that we did early on, looking at the different flights, the altitude flights of the UAV. So that's what we're seeing in the different colors here. And as we found, if we reached a density of GCPs on the ground, these ground control points, of about 2 per hectare, that really gave us some excellent vertical accuracy. That's what you're seeing on the y-axis here. We reached about an accuracy of almost 1 centimeter. So it was really great for our analyses. And from that, we can then start to create products, such as calculating the cut and fill that happened on the hillside. This was the former hillside, the farmland that was to the west of the marsh. That was cut away and then filled into the marsh here. From that, we can calculate a volume difference, which was really useful for understanding costs. And we can also calculate tidal area. So you can see in the blue, before restoration, much of that tidal area was in the creeks and the channels and in the grasslands and uplands. Post-restoration, much of that tidal area was actually in the high marsh. Another thing we can do is actually use these DEMs for calculating erosion. So as Monique pointed out earlier, the contractors on some of the banks were reinforcing these banks with channel mud. That's what was on this western bank of the main channel in phase 1. These black lines refer to the vertical profile that is over here on the side. So this reinforced channel bank on the west side eroded much less, in fact, even gained a little bit of a sedimentation between August 2018 and October 2019, versus the one on the east side, which actually eroded quite a bit more. So that resolution and accuracy in the DEM really gave us this ability to analyze this. So now I'll quickly talk about a case study of looking at the surface elevation tables versus the DEMs. First, just a quick kind of overview of what a set is. It's a deep rod benchmark that's put about 10 to 18 meters down into the ground. This is our colleague John hammer drilling one of those into place. On top of that is a table or an arm that is horizontal to the ground and through which we put these 9 pins to measure the surface of the marsh over time. We come back and repeatedly measure the same spot on the ground. This is combined with a marker horizon, which is usually feldspar, which is sprinkled onto the marsh. And from that marker horizon, we can see what sort of accretion is occurring on top of that. That white band right there is the feldspar itself. So the combination of these two can give us an idea of what sort of subsidence is happening underground, and then let us know how much elevation gain total we have over time. I'll show you an example of the data. We've got 26 sets in Elkhorn Slough that we monitor. I'm not going to go over the different kinds, but we're going to look at some of these original ones that we put in back in 2006. Our rate of elevation gain is about 1.8 millimeters per year. That would be this blue line down here, this lower light blue line. This is looking at years and millimeters of change on the y-axis. You can see that it's quite a bit less than the accretion that we're getting in the dark blue, and that is an indication that we've got deeper subsidence. And it's concerning, particularly because our sea level rise rate is about 3 times higher than our elevation rate. So if we now move over to Hester, we've got 3 sets there. We're going to focus on this set number 2, where we've got a deep R set up and a shallow one. I'm just going to go over the results of our deep set. This is also it shown in the picture right here. We have these arms, as I showed, that point out in different 90-degree directions. In those arms, we've got the different pins that go down to the ground. And from that, we collect our set data. You can see that this is quite a bit different than the rest of Elkhorn Slough, where we've got a drop in elevation. This was anticipated and not surprising to us. But we can also take those individual pins that are on the ground and we can extract our DEM elevations from our drone. So I'm just going to cycle through 3 slides here. Look at the colors of this DEM. They'll start to cool, which means that the elevation is slowly dropping from year to year. This is 2 years after restoration and 3 years after restoration. So we can then grab the elevations from those pin points right there. This is our field set measurements, and this is our UAV measurements. You can see how closely they align between the 3 different sets. And by the way, these are averaged elevations of those 36 pins. So this really confirms for us that drone DEMs are extremely accurate and useful. So just to sum up here, accurate DEMs are crucial for our understanding elevation change in the restored marsh. We have multiple survey techniques that we use, but drones we find are vitally important. And for early restoration monitoring, the drone DEMs are as good or better than data from sets. I'd say likely better because they cover such a large area as well. And that's all I've got for now.
Thank you, Charlie. There are a few questions in the chat. One of them is, how's your resolution in vegetation compared to less vegetated areas?
Yes, good question. For the drone DEMs, they're actually considered as digital surface models. So the vegetation itself is going to intercept that signal. So we're not going to get the bare ground, I guess the bare ground elevation that we would get, say, from LiDAR. But sometimes you want that, actually. Sometimes you want to see that vegetation, those vegetation patterns above the marsh. So it's kind of a trade-off there. But we're still getting the same resolution, even with vegetated areas, just not the same accuracy for the actual elevation of the marsh.
There's a question from Kyle about whether you've compared the use of RTK-equipped drones with the GCP method for vertical accuracy.
Yeah, and that's something I didn't go into is in the last 3 years, we are now using RTK-equipped drones. Those are less accurate than the method that we were using, which were non-RTK drones, but with 40 or 50 ground control points on the ground. I'd say RTK drones have maybe a detection limit of 3 to 4 centimeters, whereas our older one with using a much higher calibration was more in the range of 1 to 2. We have considered increasing our calibration of our RTK to improve those results, though. But that's a good question.
And Kat had a follow-up about the veg question on could we do corrections, like, there's various papers published on where you subtract out the canopy height of the veg, and at Hester that canopy is low compared to some of our other marshes, but would it be worth doing a canopy height correction?
Yeah, that is certainly possible. We haven't tested that, but it's a great question, and I think it's something that could be done. We're also investigating LiDAR drones. We had someone come out and fly for us to give us an indication of how well LiDAR from drones can penetrate vegetation, and the results were fairly promising. But yes, Kat, that's a great point that we can apply some of those techniques. I think it's called the lean method, where you're applying an elevation correction.
which Christina Toms just typed into the chat. Could you use the lean method? Great.
Yeah, I mean, that does require, having a four-band imagery, which is what we do have on our drone. You want that near infrared so that you can actually pull out the areas of high density vegetation versus low. But certainly it's something I think that we're going to be looking into, especially as the marsh begins to colonize more and more.
Perfect. You had a couple of other questions in the chat about accretion and such, but I'll ask you to just respond to those typing it in, and I will move on to introducing our next speaker, who is Sean Mccollum, our coastal data scientist at ESNR, one of our newer team members. And he's bringing innovative approaches to analyses of drone imagery, which I think will be useful to many of you in your different systems. So take it away, Sean.
Cool. Thank you for the introduction, Beheshti. Hi, everyone. I'm Sean, and I'm going to be sharing with you how we have been using Google Earth Engine and drone imagery to track marsh restoration. And I'm going to be focusing on how we have been using this data that we collect to conduct classifications, and about how we have been improving the accuracy of those classifications with developments to our methods, and some of the findings that we've been able to generate with those classifications. So as Monique discussed in her talk, Hester Marsh has experienced subsidence and degradation due to historic agricultural practices. And our goal is not only to restore this marsh, but also to make it resilient to sea level rise. And to effectively restore these habitats, it's important for us to monitor the progress of revegetation so that we understand what practices are leading to successful revegetation and which aren't as successful. And so through that, we can practice adaptive management. On-the-ground methods have been reliable in the past, but they have a limited amount of space that they can cover within a reasonable amount of time. And so recently we've added unpiloted aerial systems, or drones, to our toolkit to be able to more effectively monitor these large areas. And so with these drones, we can survey an entire phase of these marshes. Here we have about 60 acres, and we can monitor or survey this in a matter of hours. To conduct these surveys, we need several tools to plan, conduct, and process our survey information. And so for mission planning, we use Drone Deploy to define our area of interest where we want to monitor. And with that application, we're able to generate a flight path that the drone will then follow. During the data collection, our UAS platform, or our drone platform, which we've had several of across the years because the technology is constantly developing, we'll fly through that flight path and collect thousands of overlapping images. Those overlapping images can then be processed in Drone Deploy, Agisoft, and ArcGIS Pro. We use these software to stitch together those thousands of images into orthomosaics, which are these very large, high-resolution, top-down views of our monitoring area. And as Charlie was describing in his talk, we can also use these overlapping images to model out the surface elevation of these marshes. Now, an important aspect of how these drones collect data is that they're not just taking photographs, but they're very carefully measuring the reflectance data of distinct bands of wavelengths, for example, red, green, and blue light. And it's not just limited to the visible spectrum. We can also measure near infrared light and red edge light with our newer UAS platforms. And this is really important for generating more data, and these wavelengths can help highlight certain features better than the visible spectra. And it's important that we measure each of these bands, each of these wavelengths independently, because each feature on a landscape has a unique spectral signature or pattern of relative reflectance across wavelengths. And so in this figure here, you can see percentage reflectance on the y-axis and wavelength on the x-axis. And as you can see, trees and grass reflect relatively more infrared light than visible light, whereas sandy soil reflects relatively more visible light than infrared light. So each of these landscape features has a distinct spectral signature or a spectral fingerprint that we're able to use to identify what that feature is. We can take advantage of these spectral signatures using supervised classification, which is a method wherein we provide labeled data to a machine learning algorithm, which then learns how to classify which landscape feature some data is based on that provided data. And so in our case, we're classifying whether or not a pixel is vegetated or unvegetated based on that reflectance data. Generally speaking, these models perform better with more data, and thankfully we're able to use this reflectance data to generate other data products that can help with this classification. We can calculate spectral indices, which are combinations of bands that highlight certain features. Here we have the normalized difference vegetation index, which is a index that's used to highlight photosynthetic organisms by looking at the normalized difference of near infrared light and red light. On the left, we have a true color image, and on the right, a image of the NDVI. And you can see how pickleweed is highlighted in yellow and is able to be highlighted against that background of sediment. Unfortunately, there are limitations to these spectral indices. For one, in this example here, you can see an area where water tends to pool and algae grows. And that algae, because it's also photosynthetic, has a high NDVI value. And so it can be difficult to distinguish between algae and terrestrial plants in some of these images. On top of this, we don't always have the data necessary to calculate a particular index. In the case of NDVI, we need near-infrared light that's only available from our more recent drone images. And so to compensate for the shortcomings of any individual index or feature, we just calculate as many as we can, and that gives us as full of a data set as possible to help compensate for any shortcomings of any other index. So here you can see some of the indexes that we calculate for our data set, the elevation that we calculate with Agisoft, and then texture features, including correlation, dissimilarity, and contrast, which are measurements of the variance or heterogeneity of reflectance from the landscape. And this can help to distinguish rough pickleweed, which has a lot of texture, a physical texture, from something like the sediment, which tends to be smoother. Now, we can provide all of this data together along with those reflectance data to our machine learning algorithm. And we specifically use a random forest model, which generates decision trees and then uses those decision trees to vote on what class new data belongs to. And with all of this data, we've been able to improve the accuracies of our classifications. And now we're clocking in at about 83 to 95% accuracy, depending on how much data we're starting with. And so some of our older data only has red, green, and blue, and those will be some of the data that we're reaching 83% accuracy with. But more recently, we averaged near 90 to 95%. We calculate all of those indices and data products and conduct our classifications using Google Earth Engine. Google Earth Engine is a web-based geoprocessing platform that allows us to develop workflows and run those workflows on Google servers, which takes a lot of computational load off of our own computers and lets us develop and conduct these workflows very quickly. On top of developing our workflows on this platform, we've also developed a interactive tool that allows users to conduct classifications with their drone data with no prior experience in classification or programming. And so I'm going to show you a couple slides showcasing how this tool works. Here you can see what the tool looks like once you've added data to the uploaded data. And a great feature of this tool is that you can create samples on the fly by drawing polygons. And so here, about 6 polygons are drawn to collect samples of what each feature looks like, whether it's water, wet sediment, or pickleweed. And in a matter of seconds, this tool will train a random forest classifier and then apply it to that data set. And here you can see the results of that, showing pretty accurate classifications for just 6 polygons. And ordinarily, we would develop a more extensive data set of labeled data. But here it shows that even with that limited amount of data, it's producing pretty good classifications. And so with this workflow and tool, we've been able to classify Hester orthomosaics that we've been collecting since 2018 when we initially started this phase 1 restoration. And here's a zoomed out a perspective of the classification of phase 1, showing the true color and the map of vegetation across that. With this data set of classified orthomosaics through time, we're able to assess how revegetation has progressed in our Hester restoration sites since we've begun these restorations. In the figure here on the y-axis, you can see percent cover, and on the x-axis, time. In the yellow line, which represents phase 1, you can see that there was an initial rapid colonization of pickleweed early on in those first 2 years, which then plateaued and remained consistent across years later. This reflects that the survivorship of seedlings decreases through time, and that we see early success and then worse and harsher conditions later on, as Kirsten touched on in her talk. We see a similar pattern with phase 2 highlighted, which is the purple line, where we see that rapid initial colonization followed by a deceleration, though phase 2 doesn't have quite the plateau that we saw in phase 1. You'll also notice that phase 2 has higher overall percent cover already by year 3. And part of this is that phase 1 experienced drought conditions in 2021 and 2022, which stifled the colonization of that phase, on top of the already harsh conditions that occur later on after the restoration process. Now, I do want to note that for this figure, we're using data from only compacted sites. So the overall percent cover of these sites is higher than what you're seeing here. This is just showing the most stressful areas. And speaking of compacted sites, using drone data, we're also able to make comparisons between soil treatments. In phase 1, we noticed that compacted sites, areas where the construction equipment drove over it, compressing and smoothing out that sediment, had lower colonization and survivorship than other areas. And so in phase 2, we implemented areas of ripped or tilled soil to compare colonization between ripped and unripped areas. And here you can see how using a supervised classification of vegetation allows us to assess how well certain soil treatments perform compared to others. And this is going to be very useful moving into phase 3, where, as Kirsten and Monique showed, we have lots of different soil treatments that we're planning on comparing. And so with that, I'd like to just summarize that the lessons learned from tracking marsh restoration with drones include that classifying drone imagery is an accurate monitoring strategy that facilitates adaptive management. Calculating indices and textures is essential to achieving high classification accuracies. And recruitment of marsh plants is greatest in the first year following restoration, and drought conditions further decelerate recruitment on top of those already harshening conditions. With that, I'll take any questions.
Thank you so much. That was great. I had put a question in the chat whether anyone else is using Google Earth Engine instead of Esri products, and Christina Toms indicated using eCognition to develop the Balin's habitat map, and they're going to do their first change detection soon. So that would be
awesome.
An analogous effort that we could compare to what's going on at Elkhorn. And then Connor had a question. Did you attempt to classify different vegetation types or species? And if so, how did you train the classifier to detect the different spectral signatures?
Great question. I've played around with it mainly during the development of this tool. I was focused on vegetation versus not vegetation because we were initially having trouble just detecting that because the sediment can be pretty spectrally complex and confusing. So I've played around with it, achieved not the best accuracies so far. This next year, we're going to be trying to develop that further. One of the issues is that in these restoration sites, they're predominantly pickleweed. So there isn't a lot of data to train on for things like Frankania or Spiracularia. And where there are patches of those, they're very small. So it's hard to find them, and then it's hard to collect data on them. And so I think if we focus on a different site that's more diverse, we can build up a data set of what Spergularia looks like, what Frankenia looks like, and then use that data to apply to these marshes to try to figure out what that actual diversity is like. But that is on the docket of things that we're going to be trying to use with this tool for.
Perfect. Well, thank you. We need to move on. There was somebody who would love to see your SOP, so you can get in the chat in there and
Totally
talk to them. So our next speaker is Levi Robbins, who is a graduate student at UCSC, advised by Margaret Zimmer, who is now, unfortunately for us, primarily based at University of Wisconsin, but her team has really shed light on the importance of groundwater dynamics to Elkhorn Slough marshes. And so we're very grateful to have Levi representing that expertise here today. Levi.
Okay, hi everyone. Like Kirsten said, my name is Levi, and I'm a graduate student at UC Santa Cruz. And I'm currently researching the role of subsurface hydrology out at Hester Marsh. So let's get into it. To get into some of the motivation for why I'm doing the research that I'm doing, it's really important to talk about just how spatially heterogeneous revegetation is out at Hester Marsh. And what I mean by that is that there are clumps of pickleweed within the marsh that are super densely vegetated, and then right next door, there's nothing. It's completely bare. And in conjunction with that, we have noticed out on the marsh platform that there are areas that seem to be much wetter than other areas. So we want to investigate the connection between some of this spatial patchiness of revegetation and water within the marsh platform itself. So here's a kind of zoomed in imagery of some of this patchiness. Up here in the top, we've got a super dense patch of pickleweed, and then just next to it is absolutely nothing. So how can it be, that areas directly next to each other are doing so differently? And that leads us to my research questions, which are how does soil composition and water influence revegetation? And then what drives water availability in the subsurface? So I have a question for you all, which is, you can type in the chat, do you think that wetter areas in Hester Marsh tend to be more or less vegetated? And you can answer that as I keep presenting here. So here's just a quick little sitemap and kind of a methods overview. So we chose transects in vegetated and bare areas, and we were looking to identify distinct differences in both soil composition and water availability between these vegetated and bare transects. So in the top here, we have a vegetated transect going through a really dense patch of pickleweed, and then right next door, we have a bare transect. Along these transects, we conducted some different testing, the first of which was sediment sampling. So we took sediment samples along vegetated transect. Here's one of them here, and along bare transect. Well, here's one of them here. So we're looking for differences in the soil composition between these transects. We also placed groundwater wells along these transects. We were looking at the groundwater levels to see if they differed between vegetated and bare areas to give us an indication of water availability for pickleweed. And we also used a tool that allowed us to see soil moisture above the water table on a time series basis. So we were going out there and taking these measurements around weekly to see how soil moisture changed above the water table throughout the water year. So getting into some results, the next few slides will be results, and they will all contain figures that have this red and blue-green coloring. So I just want to highlight that here now. The blue-green coloring represents vegetated locations, and the red-pink coloring represents bare locations. So in these plots, I have gravimetric water content, which is a measure of soil moisture, and I have salinity over 2 sampling dates. And what we found was that, especially in June, the vegetated areas had much higher water content in the shallow subsurface, so 0 to 5 centimeters below ground surface. Whoops.
While you're going back, I can tell you that people in the chat correctly predicted that. When you asked them, there were they expected more vegetated in the wetter areas.
Wow, people are super smart. That's what I would predict it as well. But let's get into if that's the case. From these soil samples, it does seem to be the case, right? So vegetated areas do seem to have more soil moisture. And we also found that vegetated areas had much lower salinity. So you can see over on the right-hand side of this figure, both in June and October, the 2 sampling dates, vegetated areas had much lower salinity in the subsurface. Okay, so getting into some of the more hydrology-focused stuff, this is a time series of water levels from 2 wells, both in the lower Marsh area of phase 1. One of these wells, the one in blue-green, is in a vegetated area, and the pink-red is from a bare area. So they're roughly supposed to be equivalents of each other, both in the low marsh, just in different, very different vegetated areas. And what we found is that there's not really a difference. So there doesn't seem to be a pattern here as far as whether the water table is closer to the surface on the vegetated areas versus the bare areas. So on this y-axis here, we have elevation above sea level. So the higher you go on this y-axis, the closer to the ground surface you are. And there just doesn't seem, there's no relationship that we could find. Interestingly enough, though, we did find a relationship in soil moisture above the water table. And so this gets into some water retention stuff, thinking about how the soil on the Marsh platform holds onto its water and how it might be benefiting specifically pickleweed revegetation. So here's another box plot, and this is showing gravimetric water contents that have been taken on a around weekly basis at depth in these wells using an instrument that people are welcome to reach out to me and ask me more questions about. But the main thing to focus on and to take away from this figure, again, is that vegetated areas had much, much higher gravimetric water content in the subsurface than bare areas, which meant that more water was available in the root zone, potentially for growth. So why are these vegetated areas holding onto their water better? We really wanted to kind of assess the mechanism behind this and think about why that might be the case. So we took soil samples at depth next to these groundwater wells and looked at the relationships between the soil moisture and 3 soil parameters, sand, silt, and clay. So looking at the texture of the soil. And we found that water content increased with less sand. So that's this top plot here. Higher values of water content are at lower values of percent sand in the soil samples we took. And that water content increased with increased percent silt and increased percent clay. So higher values of gravimetric water content were located on the right-hand side of these lower 2 plots. So how does that relate to these vegetated versus bare areas? We found that there is a relationship between soil texture and water content, but we wanted to see, like, does this soil texture, the sand, silt, and clay, differ between vegetated and bare areas? And in fact, it does. So again, we've got the blue and red coloring scheme, and we found that vegetated areas had less percent sand, right, which was responsible for less water content in the subsurface. That's this upper plot. And vegetated areas had more percent silt and more percent clay, meaning that they were holding onto their water better because of this increased silt and clay content. All right, so revisiting some of revisiting the research questions that we started out with. How do soil composition and water influence revegetation? We found that revegetation is associated with A, lower salinity, and B, higher water content in the subsurface. And then what drives this water availability in the subsurface? We found that less sandy soils retained water better, and these less sandy soils were located in vegetated areas. So I'll end with just some takeaways and some lessons learned from my subsurface hydrologic study out in phase 1 of Hester Marsh. Number one, despite the salinity adaptations that pickleweed has, it still did better in areas that were less saline. Number two, water availability plays a critical role in revegetation, and this water availability is largely dictated by soil composition, not necessarily a groundwater influx, where less sandy soils were retaining water better. And that's all I have for you today. I'm happy to answer any questions.
Thanks so much, Levi. There's a couple of questions. Christina Toms was wondering whether what's happening in your wells is influenced by the tidal conditions in the previous week, like a neap tide versus a spring tide series. Did you see any evidence of that?
So yes, groundwater levels or the water table level in my wells on the Marsh platform were definitely influenced by tides. However, the spikes in water level that we saw from really high tides or inundations of the marsh itself were much shorter lived than precipitation events that resulted in a larger groundwater influx coming into the subsurface.
And then Ivano Aiello asked how the presence of water affects redox properties or the mobility of metals that can limit plant growth. Any ideas about that?
That's a great question. I'm not sure I have the answer to that one.
And finally, Ingrid asked, do you think there might be feedback loops from the vegetation back to the soil characteristics again when you're comparing those vegetated to unvegetated areas?
Right, absolutely. Increased vegetation increases evapotranspiration, which can actually lead to a dry down effect in the subsurface. So it's interesting that we're seeing higher water contents in these vegetated areas despite that increased evapotranspiration. So that's probably a direct link to the soil texture holding onto that water despite the increased evapotranspiration.
Thank you. Excellent. And it's ready for one more. Any thoughts on adding in nutrient availability or nutrient content as another potential factor affecting the vegetation?
Yeah, I think that's a great idea. Unfortunately, I'm at the end of my time as a graduate student here at UCSC, so I'm just a master's student. It's pretty quick here. If I was adding on like another chapter, I think that would be a great idea. There's always room to build off of this. Thanks, everyone.
All right, then it is a delight for me to introduce our next speaker, who is my academic daughter, Kat Beheshti, who worked with us at Esner and UCSC before a stint at OPC, and then moving to her current position with UC Santa Barbara, monitoring restoration, marshes, and kelp forest in Southern California. She's been the leader behind Elkhorn Slough eelgrass restoration and has demonstrated how successfully it can bring back ecosystem services and how rapidly. Kat was recently honored by the Cronin Award from the Estuarine Research Federation, recognizing her early career achievements. So we're proud of that too. Kat?
Thank you, Kirsty. You're making my hands sweat and I haven't even started. Okay. So today's talk that I'm going to be presenting on is on eelgrass restoration that we've conducted in natural and reconstructed tidal creeks. And our project team here is listed on the bottom. I am but one. And I just want to acknowledge up front that this team is incredible. They're actually out there. They're not out there. They're on Zoom right now, but they've been out there all week with the help of reserve staff, skippering and helping them get from site to site to execute our year one monitoring at the Hester Marsh complex. And so, again, like we could not do any of this work without the support of the Elkhorn Slough Reserve and Elkhorn Slough Foundation staff, all the volunteer divers, and our funding sources. And if at any point there's any questions that we don't have time to get to during today's time, we have all of our emails listed here, and I can also put them in the chat at the end of the talk. Okay, so let's jump in. So aerial imagery from Elkhorn Slough tells us that the system supported around 25 hectares of eelgrass habitat in around the 1930s. To support the growing needs of the canneries and whaling operations, the Moss Landing Harbor was constructed in 1947, and that artificial mouth of the estuary that was needed to create the harbor allowed for year-round fishing traffic in and out of the system to the open coast. And we saw that by 1980, based off of aerial imagery, that eelgrass extent in the system had dropped to around 2 hectares. But coincident with the recolonization of sea otters into the system, eelgrass continued to expand throughout the estuary despite high nutrient loads associated with the surrounding intense agricultural activity. That said, the recovery of eelgrass plateaued starting in around 2010, well below the historic levels around 25 hectares. And so our group was really interested in seeing whether or not we could actively restore eelgrass to hasten its recovery. The assumption here being that eelgrass germination is rare, and most of the growth and expansion that we observed was rhizomatic and occurring within the existing natural meadows, which have a depth limit. And the success of eelgrass restoration projects is rather bleak when you look to the literature. So there's a review by Van Katchwick that was published in 2016 that I often cite that reported that only 37% of restoration projects succeed, with even lower success rates for smaller scale restoration projects like the one that we conducted from 2015 to 2016. And all the results from that work are reported in our ecological applications paper that's cited in the bottom corner. So I'm not going to go into the details of that, but I do want to show that, not only did this restoration hasten recovery towards historic levels, but it also expanded the distribution of eelgrass in the system farther than it had ever been previously recorded based off of the aerial imagery. So what I'm going to show you now is a map. There's going to be yellow points that indicate our 50 by 50 centimeter restoration plots. At least that was their initial size. And overlaid, those points are going to be overlaid on a map using data from the State of the Estuary report that's produced by reserve staff. And this is from 2021. So that's 5 to 6 years post restoration. And so you can see the areas in green indicate the areas that Charlie and others have mapped as eelgrass habitat, and then you can see our yellow dots. And I've put a little inset here from the 1980s just as comparison to see how that distribution has shifted up the estuary as the years have gone on. And what happened was these very small experimental plots expanded and coalesced into one another, forming these extensive large meadows that are now being used by, some of our more charismatic to many residents of the slough, like the southern sea otter, that you'll find tens of them from a single raft using these restored meadows. And so it's really neat to see the success of this project and how it has, while small in scale initially, has had a large impact on eelgrass in the system more broadly. And so now we are asking questions about eelgrass restoration in new places, mainly tidal creek habitats. And to my knowledge, this is an area or a habitat type that is relatively unexplored as a potential area for eelgrass restoration. Most people think of well-flushed main channels as areas, or lagoons or bays as areas for eelgrass restoration, not really sinewy, sometimes poorly drained, turbid tidal creeks. And so this is work that's being led by myself and Natalie Rossi. And here we're asking, can restored eelgrass persist in tidal creeks? And if so, does restored eelgrass in tidal creeks mitigate erosion or enhance biodiversity? And the really neat thing about this, and a big silver lining to a lot of the construction delays that Kirstine and Monique had to grapple with, was that we were waiting to do this work for years. We wanted to wait until phase 3 was completed because we had mapped out doing restoration work in each of the 3 phases so we could compare their success. And in that time, the years that we were waiting for phase 3 to be completed, we actually expanded our project to include multiple collaborations. So this includes my PhD student, Hannah Lyford, who's asking whether fish and invertebrate species lists that are captured through eDNA techniques capture more species than our traditional methods, which are currently baited shrimp pots and minnow traps that they've spent the last week collecting data for both techniques, the more traditional and the more nascent techniques like eDNA. Hannah's also asking, do functional traits change post-restoration from the donor population? So when you move eelgrass from Seal Bend, for example, to a Hester Creek, does the actual morphology of the chute change and is it plastic enough to change to adapt to the conditions of a tidal creek, which are very different than the main channel? And then lastly, Elizabeth Sellinger and Melissa Ward are asking whether carbon sequestration ability differs in restored versus natural meadows, and what factors influence that carbon storage, and what are the sources of that sedimentary carbon. And so this has been really neat because it's really expanded the scope of the project that already seemed pretty broad and multifaceted. And but of course, for today's talk, we're going to focus on that core monitoring work that's being led by Natalie and myself. And I say being led, Natalie's doing all the work. I'm just behind the scenes analyzing the data in a classic PI role, not doing any of the fun stuff in the field. All right, so how do we restore? First, we harvest from a donor meadow, that's Seal Bend. Then we trim the shoots to prepare them for planting. And then we transplant. And we do this all on scuba to minimize disturbance. And we use a garden staple technique. And each of the experimental restoration plots for this work are the same size as the prior studies. They're 50 by 50 centimeters. So this time last year, we transplanted over 1,500 shoots in high and low density plots. This required, across our team, 50 total scuba dives. This project expanded years ago with funding from Ducks Unlimited, who funds the restoration in natural tidal creeks that fall within the Moss Landing Wildlife Area as part of another project that they are working on. And so this further allowed us to expand our research questions to include comparisons of restoration success and performance in constructed, or reconstructed, that would be Hester, versus natural tidal creeks, which would be the Moss Landing Wildlife Area. And those are indicated in the map on the right in green and yellow. So then after the initial transplantation, we monitor. And so for our broader research group, though, we monitor a diversity of metrics that are related to the questions I outlined earlier. For the sake of today, we're going to only be focusing on these 3. So survival and expansion, creek erosion rates that are related to the can eelgrass mitigate bank erosion, and then species richness and abundance. And before we get into the results, I just wanted to prompt you all to put in the chat an answer to the following question. Which of the following 2 habitats would you expect eelgrass survival and expansion to be highest? Restored, reconstructed tidal creeks within the Hester Marsh complex, or natural tidal creeks within the Moss Landing Wildlife Area? Or do you anticipate there to be no difference between the 2 creek types? I'm going to give you a second to put that in the chat. And while you're doing that, I'm going to move to the next slide to just orient you to the figures that are going to give us our, oh no, I'm not, because that's the header gives you the answer. So So what I'm going to show you next, I will just do it this way so more people can put their answers in. Hopefully you didn't see. So what I'm going to show you next is two figures. The figure on the left is going to be the proportion of plots that were monitored at each of the monitoring points, excluding this week's, because that data is not yet fully collected or entered. So the proportion of plots that were monitored that succeeded or persisted. And we're going to show a time series of that across those 3 time points for both Hester and Moss Landing Wildlife Area. And then we're going to show another plot on the right of a time series of chute density for those 2 creek types. The restored, reconstructed Hester ones, they're going to be shown in yellow, similar to the map, and the Moss Landing Wildlife Area creek shown in green. Okay, so this is what the figures are going to look like. I'm going to populate the data now. The headline or the title of the slide kind of gives away my punchline here, but the figure on the left shows the dashed red line that indicates the average success rate reported by Van Ketwick. So as reference, just to see how are we doing in Elkhorn Slough relative to, you know, this more comprehensive meta-analysis that assessed success. And so we see that the restored plots at Hester performed better than the restored plots in the natural tidal creeks, which honestly was really surprising to me. I did not expect that, but it's very interesting. And this is like very, very, very fresh off the press. So I haven't had time to really delve into the nuances that might be underlying all of this. So if you have any thoughts, I'm all ears. But you see that, you know, while we saw initially higher plot failure at Hester, it is kind of plateaued and is similar to Moss Landing Wildlife now. And who knows what the data look like now. Maybe Natalie and Hannah, if they have some like anecdotal evidence from what they've seen so far, can put in the chat what they think the next monitoring period will show, which is going to be August of 2025. And then in terms of chute density, what's really interesting is that chute densities at Hester are also higher. And having dove in both these spots, I don't think it's light availability because Hester's typically more turbid, so I'm not sure. I also wanted to take just a second to briefly acknowledge that we did these different transplanting densities, and that's often a big question is what density should you plant at? And really, transplant density is a balance of the advantages of planting more shoots with effort, right? And what we saw was higher initial survival of our high density treatments or plots versus our low density plots. And I'm calling high density here 46 shoots and low density 20. But we saw no long-term advantage. And what I mean by that is that the chute densities converged over time to a non-significant, and they were not significantly different from one another. And that indicates that planting more while you get higher survival initially, it doesn't give you any structural habitat complexity advantage that you would expect, at least not in the longer term. In terms of erosive processes, we also found that there was really no difference in erosive potential or mitigating erosive potential in restored versus unvegetated areas. And so for this, we used clod cards. This is Natalie on the right, assembling them at the reserve. And we've used clod cards in the past at the slough as a proxy for erosion potential, and again, detected no difference between these two habitat types. It's likely the case that the restored plots are too small to mitigate erosion, and it would be great to monitor creek geomorphology over time in creeks with versus without eelgrass using the techniques that Charlie and Sean outlined to more concretely answer the question of whether eelgrass can slow bank erosion in erosion-prone creeks. In terms of species richness and abundance, preliminary results show that invertebrates and fishes and the occasional visiting otter may be more abundant at Hester than the natural tidal creeks. And with the exception of sea otters, that synthesis of the results is based off of catch per unit effort being higher at Hester than Moss Landing Wildlife Area, though richness is comparable between the two habitat types, which is similar to what Kirstine said about reporting the fish monitoring that's been done in the Hester Channel, separate from the restoration of the eelgrass that showed that the communities are comparable to the natural reference areas that are also monitored. And so to review the lessons learned from this work, I think the biggest lesson learned is it's worth trying. Restoration success is possible in these tidal creeks, and so it is a potential area that we can look to restore in other systems and has been underexplored in the past. Also, we saw that higher density yields initially higher success or survival, but lacks longer term benefits, and that certain ecosystem services like habitat provisioning are quickly enhanced with restoration. And we've seen this with all 3 restoration projects that we've done in Elkhorn Slough thus far. And there's other logistical insights, marking plots is key. Low tide scouting prior to diving really saves a lot of time. And also, this is not a really novel lesson learned, but this is just another instance of it where site suitability and location is more important than transplant density. And so if you're trying to guard against plot mortality, it's better to prioritize finding suitable sites than planting more in areas that might be more inhospitable to eelgrass. And that's all I've got.
Thank you, Kat. You have people in the chat wondering about what is different between these 2 sets of creeks. Christina Toms wanted to know if you measured turbidity or suspended sediment concentrations between the 2.
We did not. Yeah.
And I put a comment speculating that maybe water quality is better in Hester Creek because what it's draining is this clean sediment area, scraped off the hillside, and it's high versus draining a low sort of goopy eutrophic marsh. Is it possible?
I think that could be possible. It's just, and Natalie and Hannah at this point have dove in both those creek types more than I have. So maybe they can put in the chat their thoughts, because the visibility is better in the Moss Landing wildlife area. And that might be because the water's moving faster. And so it doesn't, I don't know. But yeah, so I don't know. It's hard to figure out what it could be. Yeah, I don't know.
And Christina Toms was speculating about grazers, and I mean, you might explain to people there's sort of beneficial invertebrates, but there's also, herbivores. Any sense of whether either the good ones keeping the blades clean or herbivores might be different in the 2 areas?
We could look at our trapping data to look at like the meiofauna, but the epifauna we have that hasn't been a part of this project, I haven't noticed any difference in the density of like sea hares and idatea versus like harmful amphipods that might be to blame for this, or explain. Yeah, I'm not sure. I haven't had much time to think about this. So hopefully maybe the next time we all get together to talk about it, I'll have like some really compelling answers to give you. But I haven't noticed anything that would be an obvious indicator of why Hester's doing better than the others.
Hannah was just speculating that maybe distance from the main channel, is greater in some of the Moss Landing wildlife ones than the Hester ones that are pretty close. So maybe, a residence time thing or something. And
totally, that's
Andrew Welch suggested temperature, which would be then related to that.
Yeah, those are great ones. Yeah, and I think that maybe down the road, Hannah will be doing a little bit more monitoring in these plots. So it might be the case that we want to put out some more sensors that give us some sort of indication of what might be driving these patterns.
Well, thank you, Kat. And that brings us to the end of this session on monitoring habitat conditions and plant colonization. So I will